are stuck in the road traffic, including Professor Christoforou and many of the members. This panel is titled Advanced Non-Destructive and Structural Techniques for Diagnosis, Redesign, Health Monitoring and Quality Assessment of Materials and Preservation Interventions. First of all, we would like to thank Professor Moropoulou for compiling such a multidisciplinary and very esteemed panel. And this panel will show that NDTs are covering a wide range from the micro scale to the macro scale of the whole buildings. We will see that from all the talks that they cover from fundamental research to applications of NDTs. And from just my quick intervention is that I feel the future of the non-destructive testing lays in digitization. It's a challenge actually because many of the NDTs have not reached the level of other techniques that are used in other fields, like let's say geometric documentation, as I said yesterday, but we are trying to do that. The clear danger is that since our society and since our scientific community is accustomed to nowadays to virtual reality, augmented reality, that we are expecting to see same results in non-destructive testing. The danger, as I feel it, is that since we are expecting to see something three-dimensional moving around and rotating and things like that, we are losing much of the fundamental science. And many of our esteemed colleagues will show exactly that it's, we have to understand what's happening behind what is the final result, because obviously sometimes what you see is not what you get or actually how you got it. We're talking about many techniques based on electromagnetic spectrum, on visual and all this, and it's difficult to interpret the results and present them. So one of the challenges is the digitization. The other one is that we need to move to a spatial approach. We need to combine all these non-destructive results into one big platform of a structure of a cultural heritage asset, something like H-beam. We have not reached that yet because many of the techniques have not reached that level of actual georeference and so on. And the third is AI. We have the similar panels before, yesterday about AI. Again, entities, I don't think it's a clear danger that AI will substitute our profession, because much of the beauty and much of the workload on entities is how you interpret the results. AI, I don't think it has reached that level yet. Obviously, it's the future. We obviously entities section will exploit AI. They have started doing that, mostly in image processing techniques. But as our colleagues will show, it's a way ahead. So now, after that, is Professor Asman connected or not? Online? No. How about Professor Zhang Hai? No. Professor Amditis, is he connected? Okay, so Professor Amditis has the floor from National Technical University of Athens, Institute of Communication and Computer Systems. He's a research director of this institute. The floor is yours.
Thank you so much, and thank you to Mr. Moropoulou and to the conference that you have invited me. I will try to share my screen. Give me a second, please. I don't know if you see my presentation already.
Yes, we can see it.
Perfect. So, as Professor Moropoulou said, many people arrived from different places of Europe to the conference. That was much easier than us staying in Athens to navigate and come there ourselves. That's why I'm also speaking to you online right now. So thank you very much. As it was mentioned already for our moderator, I'm coming from the National Technical University of Athens, and specifically from one research center of NTUA, which is called ICCS. ICCS stands for Institute of Communication and Computer Systems. and it's related with all aspects of electrical and computer engineering science in all different areas, one of them being exactly what we are discussing here in this conference, especially looking at it from the technologies point of view. And that is why I'm going to try to discuss a little bit with you. Just for your information, our organization consists of more than 1,000 researchers and scientists right now in all the fields that you've seen on the right part of this slide. And together with NTUA, we're #1 research organizations today in Greece and in the top 20 list of Europe. So what I would like to discuss a little bit with you today, and this is of course not new, it was also mentioned by our moderator today, is all these possibilities that are opened up the increasing advances in digital technologies, which are quite impressive and ever-growing. So from 3D tech to artificial intelligence and virtual augmented reality, these are all being used not only to ensure preservation, but also to support our work, our knowledge, and our experience with our cultural monuments. So there has been an explosion, actually, of digital innovations over the last 20 years. And such technologies include 3D modeling, AI and ML, machine learning algorithms for prediction and tracking, UAVs for monitoring, gamification, also digital restoration simulations and digital twins, but also social networks and the use of information systems to support also the inclusion of users, of citizens in all our work, what we call the crowdsourcing today. So all of them are applied today, all these technologies, to preserve cultural heritage in different parts of the world. Three-dimensional digital technologies are mainly widely used in the preservation of material cultural heritage, and it has been applied in buildings of different types, such as castles, churches, sculptures, archaeological sites, among many other things. Concepts also, as the virtual museums, are being adopted more and more all around the world. The European Commission, through extensive policy, coordination and funding actions, supports member states and all our institutes and universities and organizations to even more advance their cultural policy with a special emphasis on digitization and on online access to cultural materials and digital preservation and curation. So I would like to briefly talk to you today about a couple of these projects that are being supported by a European Commission, focusing mainly on the deterioration of cultural heritage, which is becoming more and more one of the biggest challenges in conservation. Aspects like building technologies, materials, structural responses, preventive measures, and restoration strategies, resilience and adaptation methodologies are always and continuously considered. Also, we need to be able to assess quantitatively, but also qualitatively, the impact of various climate and other parameters on the sites, develop strategies, and also an overall resilience and reconstruction planning framework for all our historical areas. I will briefly mention to you today, introduce to you two major research projects, European research projects, where we are applying all these innovative technological tools in order to monitor, to preserve, and to create prediction models that we are working and we are also coordinating. So one of them, the more recent one, which is quite active right now, it's called Thetida. And Thetida is using exactly technologies with the main aim to support and to improve, if you like, resilience, especially for underwater and coastal monuments related to all issues related with climate change, with natural hazards, and other environmental aspects.
Dr. Amditis, if you can
yes.
please be a little more brief, because we need to put the floor to the other speakers and we are running on time. So if you can be very brief on each project, just to get an idea of the whole spectrum you have. Thank you.
This is what is my plan.
Thank you.
So CETIDA consists of 17 partners from 8 participating countries and has a duration of 4 years, so it will run until 2026. Hyperion, on the other side, is another project that we have been looking at also in this conference in the previous years, and has been related mainly with the effects of climate change, ravage of time, intense geological phenomena, and other related issues. So very fast, I will try to give you an overview of these things. So in CETIDA, we are looking especially on underwater and coastal monuments, where we are trying to look on coastal threats, erosion, heat drought, earthquake, and many other issues, but also underwater threats related to temperature, to water pollution and acidification. And we have 7 different pilot sites with a number of monuments, from castles in Mykonos, for example, the castle up to underwater like wrecks and underwater monuments that we are been working with. So this is just a very fast overview of the different technologies that are being used, from remote sensing to wearable sensors to autonomous underwater vehicles and to smart tags, that all of them are being utilized in order to work, as I mentioned, to the aspects I mentioned before. So this is some pictures of the work that is being done right now, as we are trying to analyze different materials, and also to look at specific issues like wetting, deterioration, seawater acidification, using different type of sensors and technologies. Very fast also for Hyperion. Hyperion was doing also something more quite interesting. I was trying to involve end users, so citizens, if you like, through platforms, in order to assess exactly, to have a better understanding of the dangers and threats to tangible cultural heritage, making decisions for a swifter and more effective response, and contribute also to the sustainable reorganization of the historical regions under threat. This is some pictures from the medieval city of Rhodos, where we have done a number of things there with sensors and with the use of with the participation of citizens. So I would like to close this intervention with just mentioning about the EU Green Cluster on cultural heritage. Already from 2021, the Commission has issued 3 different calls of proposal and has selected more than 10 research projects looking on all these aspects. And all of them together have created a green cluster in order to work together on all the aspects I mentioned before. The overall goal of the Commission is to support transdisciplinary joint efforts of researchers to develop sustainable preservation and adaptation plans. So, thank you very much. This is just a slide to show you future prospects and extensions of this work. I truly believe that the wider application of technologies that will support our work, and we have a number of aspects that we are looking today. And in this slide, you can see also a few of the items that are under investigation today. Thank you very much.
Thank you, Dr. Atmitis. And you have seen that the compilation of all this information through all these type of platforms, and these are very crucial, because otherwise all the specific fields of each entities are just isolated. We are bringing them together through platforms like presented here, in order to have interdisciplinary analysis, co-analysis of various data, so that everybody can speak the same language and understand what everybody else is doing. Platforms is the future. We should orient our specific techniques towards being accessible and usable by such platforms. Thank you. So the next,
thank you very much. Thank you.
The next speaker, the next panelist is George Karagiannis from Ormilia Foundation. He's a scientific director. Dr. Karagiannis, the floor is yours. Please present us your exciting things.
Thank you very much. Thank you very much, Professor. Labropoulos. I thank Professor Monopoulou for the invitation to be here today. I think with this, yes. I'm George Karagans. I'm coming from our Millennium Foundation. I would like to tell some things as a case for discussion. The bottom-up documentation of cultural heritage objects, not only for the conservation science, but also for authentication cases, and also for historical and aesthetic documentation of the object, which is itemography and infrastructure that we have developed in the lab, covering non-destructive documentation of cultural heritage objects. I'm going to tell about how we could organize the data based on DICOM-DE, which is the DICOM protocol. Professor Christoforou has just arrived. Okay. And how there is the DICOM protocol for the non-destructive test techniques, and how can AI, which is now already applied to the data, can support all the above mentioned work. Well, this is Ormila Foundation. I'm passing. The objective is the identification of the material and the structural composition of cultural heritage artwork, and in general cultural heritage object, using various tomographic imaging, spectroscopic, with various excitation and waves techniques. The implementation is to utilize all these methods through the corresponding devices in order to make non-destructively an object transparent and see what is the state of preservation, the corrosion, the materials, the pathology, the story, the authentication in all the bulk of the object. And the challenge is now, we have passed this challenge actually. We have designed and we have autonomous, as also Professor Avditi said before, and systems in order to make the scans and the appropriate mechanical and robotic systems in order to acquire the data from the cultural heritage objects and monuments. And now we are in the position to apply AI, artificial intelligence techniques, in all this kind of data. Well, this is the infrastructure which we have already, and this is improved from the previous time that I was here, which involves various kind of imaging, various kind of tomographies, various kind of remote sensing, and various kind of spectroscopies and combination of them techniques, which all of them now are portable. Also the mechanical scaffolds that we use for this in order to go on site, and according to the kind of the object, if it's easy to move it or not to move it, to place it in a horizontal or a perpendicular in direction, in order to scan it using all these kind of the techniques. For instance, here we can see various kind of the XY adaptable robotic system in order to have the possibility to scan using portable X-ray tomographer the various kind of the object. This was specially developed for the case of Vergina. So we are in the position, and all the teams that are working now all over Europe, we are mature enough and we are scanning objects having resolution from micrometers and the possibility to scan micrometers up to meters with the appropriate resolution in order to make tomography and material identification and, as I said before, corrosion, pathology and authenticity from micrometers to centimeters to millimeters, centimeters, up to meters, as you can see here in this transparent, even to the excavations. And I'm going, how can I activate the video?
Just press this.
Yes, this is it's too high. Maybe we can reduce the noise, the sound. This is in real, the eye tomography in situ, in the way that the most modalities were set up, and all the robotic arms, as you can see here, scanning with various systems of ultrasonics, electromagnetic waves, spectroscopies, in order to document all these very important objects coming from the tomb of Philippus II. So it's deserved to see this, and then I'm closing. You see, we're rotating the object in order to make X-ray in situ tomography. Here we identify materials, the various masses of materials coming from the tomb, assembling the X-ray tomographer, placing the object with the appropriate probes from the spectrophotometers, observing real-time the tomography, the X-ray or ultrasonic tomography in order to see with the archaeologists what is happening. You see here we are rotating again another object in order to make CT tomography. Sometimes the manual procedure is also very useful, not so, and many times we have to use it because the automatic procedures sometimes fail for specific reasons, of course. So this is the case of the in situ. I think that, yeah. And the final result is that we have documented all these kind of objects, which are, I think, yeah, it's coming from the tomb of Philippos the Vicar, the second. And as you can see here, we have a big database. Okay, no problem, I can go back. From various kind of objects from all the historical periods. And we have done work in situ all over the world. So this is I cannot touch each kind of the data. We deliver this kind of, this is a case of what we deliver. This is a DICOM file, actually, where all the information is embedded in one file. DICOM file is well known from the medical sector, from the medical scientific diagnostic field. And there is the decoder, the corresponding protocol in order to store the data from non-destructive testing technique in general. This is the case of cultural headers, where you can see all the tomographic images, the spectroscopic information. What is a decoder file is covering and describing the kind of the data that you have and the whole procedure. You can trace the whole procedure that these data are acquired and how they are interconnected among them. So we follow this protocol, which is the STM-E2339, and I want to come here, yes. And this protocol in general covers the possibility to store the data coming from all the kind of the geometries, like an artwork or an object that we scan in the industry, which involves scanning procedure, providing cube imaging, cube data, where we have the X, Y, Z information, which in the Z dimension we have the raw signal, the one-point signal, which can be an ultrasonic signal or X-ray signal or a spectroscopic signal or a reflectance coefficient, whatever. So now we are in the position to store these three or n-dimensional signals in the DICOM file, which covers the entity techniques. And we are now in the era of where we are working in order to identify the most information that we can extract from this kind of the data. So this is important, the high fidelity of the way that we are acquiring the information, to be very strict and secure in order to have a high level of data in order to use this big data, because we have thousands of data now in Europe on cultural heritage, in order to apply deep learning without involving errors or minimize the errors that we have due to the fact that we scan this with the robotic arms and the high fidelity procedures. And then now we are applying neural networks, which is actually the technique of artificial intelligence, in order to work on the conservation science, many requirements, on the authentication services requirements, on the historical and aesthetic documentation requirements that we have. And the AI can be applied, and now we are applying it, of course, in the 1D data, the 1D signals, of course, in the 2D signals, the slices, and, well, it's difficult because all of us will have to have the same way of storing the data and the same way of scanning the data in order to apply this to the 3D structure or to the ND dimension, to the many dimension structure, which involves various kinds of objects, as I told before. Here we are now, and this must be one of the targets in order the whole community work on this very powerful tool that we have due to the fact of the big data of the artificial intelligence. Thank you very much. I want to just mention that 9th to 11th of May, we are organizing the Pan-Hellenic Conference of Non-Destructive Testing Techniques in Ormilia Foundation. you are invited all to come. And there is a session also besides the industry and biomedical sector, and a session about cultural heritage documentation using non-destructive testing techniques. Thank you very much.
Thank you, George. And thank you for the AI slides. We realized that AI can actually be applied earlier in the signal processing. That's probably more convenient and more efficient because it can help us interpretation rather than afterwards when you're just trying to compile a lot of data, as you said, big data from platforms and trying to figure out what's happening. Thank you. And the next speaker is Professor Loutas Theodoros from University of Patras, Department of Mechanical Engineering. As far as I know, is he still online?
Yeah.
Hello.
I'm over here. Can you hear me?
Hello, Theodore. Yes. The floor is yours. Let's all try to be on time and just be brief up to the point. Thank you.
Of course.
Do you have a presentation or? Yeah.
Good morning. Yeah,
Okay.
I am sharing. Can you see? I think you can see my presentation.
Yes. Thank you.
Good morning, everyone. Hello, Kyriakos, and to Professor Moropoulou. My best regards to everyone. I'm Theoloutas. I'm professor in the Department of Mechanical Engineering and Aeronautics, and I will try to give you my view in NDT or SHM for cultural heritage preservation, my view on the, let's say, future events in the sense of AI or machine learning. I'm going to use these terms interchangeably. Let me tell you that we do not work directly in cultural heritage, but we have a long experience, a multi-year experience in the aeronautics and space and materials field. So I think where we use NDT and SHM many years, and the last at least 10 years, we are trying to see how the new developments, new tools and sophisticated tools and algorithms can help us do perform our tasks in an even better and more effective way. So let me not take much word on this. I think these are things that you have covered yesterday or today and tomorrow. Modern challenges, you are very well aware of this stuff. Rapid urbanization threatens historical sites, mass tourism, climate changes, and of course, the critical funding gaps that hinder the efforts that you in the community makes towards the cultural heritage preservation. The new tools, AI tools, machine learning tools come into play, and they can be very helpful and very crucial to be integrated in the traditional NDT or SHM tasks that we want to do. So in the diagnostics field, AI can, I think that it can significantly enhance with the difficult or peculiar diagnostic tasks. For example, it can enhance the detection, localization, and sizing of internal defects that are not visible from the surface. It can assist with the early detection of developing structural issues. It may detect biological colonization, for example, like mold, algae, insects, and stuff that are difficult to be diagnosed with the simple tools, let's say. You can even use it to detect incompatible restoration materials from previous interventions. Another field that I personally very much like and work in research level the last 10 years is the prognostic field. So how can AI enhance a prognostic task? And in your field, in the cultural heritage preservation field, you can use AI to integrate real-time data with prognostic algorithms that are based on machine learning. And you can predict the evolution of progressive deterioration phenomena, such as pollutant deposition or biological growth patterns. You can use AI to forecast environmental impacts. And even more, you can use it to support predictive maintenance planning. So if you want to move from the periodic maintenance paradigm and go to a condition-based paradigm, prognostics is an essential tool. It is an essential tool as well to estimate the remaining useful life of structural elements that you may use in your applications. So a possible pipeline, as we call it, could look like this. You start on one end you have raw entity data, which need severe preprocessing to remove noise, normalize data so as to ensure the consistency across different scans and scales. Then we have the step of intelligent feature extraction. This can be done especially to 2D data or 3D data. It can be done with, for example, convolutional neural networks, so as to identify and extract significant features that otherwise it's very difficult to extract. The next step comes the hardcore machine learning things, deep learning stuff such as CNN or LSTM combined with LSTM architectures, or even more sophisticated architectures like graph neural networks, more modern things. All this to recognize pattern, detect potential defects, and even predict their evolution and their progression in the materials. A last and very interesting step could be the transfer learning. So to leverage pre-trained models on similar materials to enhance the accuracy and efficiency of defect detection and classification in other materials, in other classes maybe of materials, or in other types of structures. This is the transfer learning stuff. And to close my short presentation and intervention, the clear message to the community is to share. We have to share our entity data in order, and this is understandable, because in order to form effective and powerful machine learning algorithms that can do whatever you want them to do effectively, you need very good training data. So everyone has data, but we do not have, I would say, maybe the culture to share them in an open and free manner. And this is my takeaway message from today's intervention, and I thank you very much for the invitation.
Thank you, Professor Loutas, and mostly thank you for clarifying all this pipeline of transforming raw data into something useful for AI and for further elaboration. And you're right about that, at least at this stage, the majority of the scientific community does not have still the culture of, first of all, sharing the data, but more importantly to prepare the data in such a way that can be exploitable at later stages like the ones you explained. Thank you very much for these clarifications and food for thought. The next speaker, the next is Professor Vice Rector of Economics of International Hellenic University, Professor Stelios Xanthos from the School of Engineering, Department of Industrial Engineering and Management, and we are waiting for your intervention.
Thank you, Professor Labropoulos. I will try to present you our work related not actually to the health of the structure of a building, but actually the impact of building materials to the health of people that they are visiting these historic buildings using non-destructive techniques, but also using some non-destructive testing for detecting cracks, for example, that affects our work. Our work is around radiation protection and around exposure, radiological exposure. So one of our projects, among others, had to do with estimating the radiation exposure from post-Byzantine churches in Thessaloniki, among other historical buildings. You know that the problem with these buildings is that you cannot have samples from the building materials in order to measure them in the laboratory, but have to go there and perform in situ measurements. This is our case, performing in situ gamma ray spectrometry measurements for determining the external radiation exposure and also for estimating the internal radiation exposure. We are measuring radon. Radon is a radioactive gas, a natural radioactive gas. Mainly, what we are measuring is natural radioactivity, and of course, it is not nuclear radioactivity coming from technical artificial elements. And these are some of our. These are the 8 post-Byzantine churches that we studied: St. Athanasios, St. Antonios, St. Gregory Palamas, Παναγία Λοδηγήτρια, St. Minas, Νέα Παναγία, Παναγούδα, and Ipapante. So what we are interested in is finding what we are calling sick buildings. Are the historical buildings sick buildings? We have to see this. Okay, this is the definition for sick building syndrome or building-related illness. It's building occupants experience acute health and comfort effects that appear to be linked to time spent in a building, but not specific illness or cause can be identified. So we have to test actually the building materials that they are built from. What we are interested in measuring is the indoor air quality. We are focused on radioactivity from building materials, radon, gamma radiation. When we say indoor air quality, we mean particulate matter. And of course, some others that we are not interested in is chemical contaminants and biological contaminants, that they are not so serious for human health. Okay, this is in order to show you what is the mean average dose the people worldwide are exposed to and are taking. You can see that over the years there is an increase of due to medical treatments, increase of dose due to medical treatments, and also you can see that the most significant part is radon exposure, the air radioactivity in air, that is in indoor areas mainly. So this is to show you a laboratory that that performs gamma spectrometry measurements. Okay, and this is what we're measuring, what we want to identify. It's lead, 212. This is the radioactive elements: bismuth, actinium, potassium 40. We ourselves, we have potassium 40 in our body. Thallium 209 and artificial one, that is cesium-137, that comes from Chernobyl accident. This is what we're measuring. But if we want to measure radioactivity, we have to take samples from the buildings. This is the geometries that we are using. This is not the case in historical buildings, so we have to perform in situ measurements in order to estimate radiation exposure. An alias to us is that we have also simulation. Simulation is a very critical thing to our work because we can easily, with simulations, extract the factors, extract the coefficients in order to convert radioactivity to dose exposure. Also in some non-destructive testings, For example, when we want to perform an X-ray in a column or in a building material, we can find the perfect adjustments to our X-ray tomography or to our radiation source. We can use radiation source and detector also in order to see what is inside in a column, maybe iron or whatever. And with simulations, we can have much more information easily, and we are exposed less to radioactivity, to radiation. This is the radiological risks and what is the recommendation from EU for building materials, external dose and internal dose from radon. What is interesting here is that the risk factor is 5.5% per sievert. That means 5.5% having exposed to one sievert, they will have a lethal cancer. So you see how important it is to measure radioactivity in buildings, even in historical ones. These are instruments to measure radioactivity from home, let's say, detectors to more sophisticated one, pacific and active ones. This is the radiological risk for radon intake, and this is, as you can see, for every 100 becquerels per cubic meter. The limit is 300 becquerels per cubic meter. For every 100 becquerel, this is 16% increase of radiation of risk. And this is an instrument in order to measure particulate matter, the indoor air quality, the way it operates, the principle of operation is this one, a laser in a chamber, a dark chamber, reflection to the dust of the laser beam, and then the photodetector detects the light. The more the dust, the more the signal from the photodetector. These are the regulations from EU. What is interesting here is that for every 100 micrograms per cubic meter of particulate matter, of PM10 for example, the lung cancer rate roses 22%. And okay, of course, we are monitoring this using low-cost microprocessor, an Arduino One with GSM, in order to send the data to the laboratory and then to present the data to a platform. We are oriented to open data treatment, and also our work, finalizing my presentation, we are interested in cracks because from cracks radon exhales to indoor air, so we want to automatically detect them and erase all the other things that they are in the marbles or in the stones and so on. So we developed some, let's say, image processing techniques in order to eliminate all the other holes and so on that we are not interested in, or some other holes, or even some plates that we want to eliminate, and just hold the cracks. And also, of course, using infrared monitoring in order to see energy loss from these historical buildings. Thank you.
Thank you, Professor Xanthos. And this is a demonstration that entities cover a really wide spectrum of scales, techniques, spectrum, and so on. So this is the beauty of this panel, that you can see from big research centers to fundamental research by universities, and covering the whole range from small to big to structures. So don't get used that entities are in the field just climbing on a structure and trying to do things. We have laboratories that excel in this research. We have about half an hour left, so I urge the remaining speakers to be as brief as possible, so that we give the opportunity for Professor Xaforu to wrap up everything. No, not now, after the end. So the remaining three speakers, unless Professor Osman and Hai are online, try to be as brief as possible. So the next speaker is Professor Nicholas Prematikos from the University of West Attica, Department of Civil Engineering, and he's going to present us his own perspectives of NDT.
Thank you very much. Hello, everybody. I would like to thank also Professor Moropoulou for the invitation to be here with you today. A lot of things have been told, so I'm not spend a lot of time. I look the subject from the way of civil engineering, and just to say, we speak for destructive, non-destructive, or semi-destructive testing. We have to cover a whole area for examination and use the data not only to measure some material properties, but to examination. We use destructive for examination, for inspection, or for evaluation, or retrofittive techniques after the construction and the retrofitting. And of course, the philosophy is to measure some property which is related to another one, but we sometimes don't don't forget to take account the environmental loads in the structure. I mean, what kind of conditions is in static load, is in dynamic load, is in fatigue load, and have into consideration this. Also, the environmental aging due to climate crisis accelerates a lot of aging and damages to the structure. There are a lot of methods, a lot of tests. I don't want to mention that are very well known. What I want to say is we should kind of merge these techniques, or to combine a lot of times some these techniques to make some more reliable results, and a combination. And we should also link the expertise of those who involved and link together, because they look sometimes in different directions. Also, there is a subject for methods in small scale or in upscale, in situ, as already mentioned, and also in, as we say, common language for different people, for different directions. We should link all of them together. Chemical, mechanical, electrical, civil engineering, architecture, archaeologics, historians, material science, surveys, all of them should speak in a common language. This, of course, drive us in an education issues and all, how to understand each other. And another big issue is, as again already mentioned, is about a lot of data from all these tests, and we should manipulate all this data using AI tools, deep learning, machine learning, and all these things, all these tools. So not only to manipulate in order to repository them, but in order to manage to be this information accessible, understandable, and useful for everybody for those categories that I mentioned before. So we have also to think about how this data will be accessible and understandable, and this also drive us again to education level of in the group of science, in the group of practitioners, in the group of technicians, how they communicate each other. So other thoughts, I don't want to say a lot. I close saying that it's a good to have, like in beam technology, like a federal model which include all these informations, where we have the geometric model, we have all the analytical information of each piece of this. So all this information, all this data should be included in a federal model with multi-layer information of levels, and this will help us to have a better picture and to intervene in more precise and effectively way. For this, thank you very much for your attention. I'll be...
Indeed, Professor Emblematic was right about that, about the education on NDTs. I think the Hellenic Society of Non-Destructive Testing in Greece plays a crucial role in that, and standardization.
Yes.
Because we need to listen to other scientists and they need to listen to us.
Yes.
So communication before we actually present results. The clear danger is that the future generations of engineers may be accustomed to something that is already prepared through AI, through automation and so on, and they lose all the science and all the physics and all the analysis for that, and they may misinterpret things without really understanding that.
Exactly.
Thank you very much. On behalf of Professor Matikas, who could not be present with us, we have Dr. Dimitris Exarchos from the University of Ioannina, Department of Material Science and Engineering, Laboratory of Mechanics, Smart Sensors and Non-Destructive Evaluation. And he... Do you need that?
No, I don't have a presentation. Professor Matikas, first of all, I have to say his greetings. He's in a trip with International Atomic Energy of United Nations and Tunis, and that's why he cannot be present with us. And also he wants, first of all, to thank a lot Emeritus Professor Moropoulou for the invitation, and he hopes that with the new emblematic action Evlogon, that we will have a even more close collaboration to the non-destructive evaluation of monuments and cultural heritage protection. When he told me that I have to be on his behalf, I asked him if he wants to make a presentation, and he told me, no, don't make a presentation, it's a panel, and you will understand when you are up there that why you don't need a presentation. And it is clear that everyone before my part of talking, he has already discussed many advanced non-destructive techniques. The idea is not only how we make new advancements in non-destructive evaluation of cultural heritage, but what the last speaker said, how we can all of them merge them together, how we can find the best results of it, and how we can all of them involve them to how we can make a better preservation techniques, how we can convince other, we are from the side of mechanics, okay, we can understand what it needs to happen, but it is an interdisciplinary aspect. We have to convince, for example, archaeology that we need to introduce inside the monument some sensors and to have a real-time monitoring of the condition of the monuments. Also, we have to take in consideration how the different non-destructive techniques become better and how we can have some of them even used in real time. I mean, if we can now, there are technologies that allow us to have very cheap non-destructive sensors embedded in monuments. The bigger problem there is, again, how you can take how you can convince archaeology and everything to embed them in the monuments. I think that it is part of our work, our job, except the research, is to have a fruitful discussion with all the needed parties and find a way to implement all these very good, very international accepted work that we do to make it real in the monuments, not only in our country, but everywhere in the world. I don't want to take too much time more. I want just to say that because this session has 4 aspects. It is the advancement in non-destructive techniques, the structural techniques for diagnosis and redesign, and the health monitoring. For example, for Dr. Karakiannis, what they already do is amazing. I don't know if you use a 3D model of the icon or you just use a digital image. In the case that is needed, yes, we can. For the paintings, no, but yes, in the case that is needed, we use a 3D model. Yeah, because that is even a step higher, because maybe even in an image, at least we have found some an image that was from the 2 sides painted during the centuries. They have painted even the back side.
Yes, of course.
And we made a 3D model of this. And okay, there it is even more difficult to introduce all this data, but I think that's the future also for not only mainly paintings is not the only thing, but imagine anything from the archaeological side that you can have the 3D model and in each side you have the whole information of non-destructive evaluation of the object.
The issues there are the registration issues.
Yeah, definitely it's the registration, but we are here to try to solve all of that. And also AI, I say I'm a bit probably younger from all of the others here because it wasn't my position here. AI is a useful tool. We don't have to demonize the AI. AI is the future, at least at the moment. We don't know what will happen in a few years, but AI solves many problems in a very, if you know how to use it, and if you do the machine learning correctly, solves many problems in a very quick way, in a very accurate way, many times even more accurate than a human can do. Thank you very much. I hope I was on time.
Thank you, Dr. Exarchos. And I think you just press a button about cooperation. At least in cultural heritage, the biggest difficulty is how the non-destructive techniques community can convince archaeologists or people that don't understand much of engineering that we know what we are talking about. Obviously, with the development of NDTs, things are getting better because we don't need to teach them how to read a radiogram or something, a very specific technique. Nowadays, we give them final results that are easily understandable, easily they can be understood, taken for granted much easier. So the floor now is on...
Can I say something here?
Yes, please.
You know even better than me that there is, in order to apply a non-destructive testing technique in the archaeological objects,
you have to ask for a special license from the Ministry of Culture. And the question here is, we have so many portable modalities that are very useful and on the field, so that the restorer or the restorer mainly can take some measurements fastly in order to make a fast decision. This is not so easy to stop, ask for a license, and then come back and take the measurement and show the results. And then after showing the results,
anyway,
use them.
the situation is improving. Cooperation is much better because we have shown them the merits of these entities techniques, and things are getting better. And this is the future that, since we have platforms and we integrate all the information, they can appreciate it much better nowadays, and things will get better in the future. So, Professor Christoforou, you have about 15 minutes. You have the most time among us to present your perspective and to wrap up of your of the panel of what you have.
Okay, thank you very much.
He's obvious, I forgot to say, to introduce him, Professor Christoforou. He's from the National Technical University of Athens, School of Electrical and Computer Engineering, and he's represented from the Hellenic Society of Non-Destructive Testing. So he's the most appropriate person to discuss about the whole, the big picture of NDTs and in Greece. And thank you very much.
Thank you, Mr. Chairman. First of all, I think that there are several people in this room and in the audience, the remote audience, I mean, that are excellent in performing NDT, and especially in NDT for cultural heritage. You will allow me to present with a few words the activities we are running these days in cultural heritage entity technologies in the laboratory, in our laboratory, and then I will be honored to sum up things we heard during this panel session. Well, to those of you who know about the activities of our laboratory, the Laboratory of Electronic Sensors of the National Technical University of Athens, we are mainly doing magnetics. We work on magnetic technologies for the still health monitoring, and due to this activity, in the last conference in this very place, we presented technologies related to monitoring the structural health of metallic, unseen metallic, items. And I think this was rather not at the very central focus point of the conference. However, today I have the pleasure to present you a new technology we are developing in the laboratory concerning, as you can see the slide, concerning another activity which has been initiated in 2021 in our laboratory, which concerns optics and plasmonics and for cultural heritage. Actually, we use optics and plasmonics not only for cultural heritage, but also for continuous emission monitoring, for bio applications, and for agricultural food tests. But it's also usable, as you will see, for cultural heritage studies. So, during these years, we have developed our own instrument, which I must say it is somehow inexpensive and can be used in remote areas. This means it is portable and can be connected with cell phone, with laptop, etc. How it works? It uses a laser source as an input signal, laser source or white light source, which excites the material under test, according to which you can according to which fluorescence and absorbance as well as scattering are developed. And absorbance and fluorescence can be actually detected by a Hamamatsu microchip reducing dramatically the cost and the size of the instrument. So, using this technique, we are able to monitor fluorescence and absorbance. Apart from that, we also use a carefully selected camera, which can be used to measure the scattering of the light, either laser light or white light, LED white light. In the beginning, we have initiated the first generation device, which was limited from visible, let's say 400 nanometers up to 950 nanometers. However, during the last 2 years, we have developed the second generation of this device, according to which we can detect fluorescence, absorption, and scattering from 200 nanometers up to 1200 nanometers. A little bit more than this slide says. And this we have done thanks to the pioneering work of Dr. George Violakis, collaborating with us from the University of Creta. According to this arrangement, we were measuring cultural heritage stuff, like we gave emphasis actually in paintings. So with these devices, we observed classical fluorescence and absorption responses, which actually didn't give the precision, the sensitivity that we wanted to achieve. For this reason, we entered in deep waters. Deep waters means we entered in plasmonics. So what we wanted to do is to enhance, to amplify these signals coming out of the fluorescence and absorption measurements. And to actually be able to see how plasmonics can help you in that way, you must understand how the plasmonics operate. And allow me to say, to explain in simple words, how the plasmonics enhanced our measuring ability. You know, plasmonics is the following thing. You have a dielectric base matrix in which you apply with a matching handle, let's say, in certain positions, metals. Metals in sizes of from 10 nanometers up to 100 nanometers. This way, you are able to generate electric, you can generate electric density, higher electric density at the boundaries of the metallic dots, and therefore any kind of light excitation, this means fluorescence or absorbance excitation, is used to amplify the motion of these electrons, which in turn generate secondary waveforms that can be detected by the spectrum analyzer I described before, the Hamamatsu chip, if you remember. For this reason, we have developed our own plasmonic films based on silver nanodots. These silver nanodots have been made by plasma spray technology, and this way we can say that we have controlled the production of 20 nanometers plus minus 2 nanometers diameter and powders from 30 to 50 nanometers, more or less, with a normal Gaussian distribution, and finally silver nanopowders up to 80 nanometers. And the whole spectrum of this size of silver nanometers allowed us to have an amplification of the fluorescence and absorption response from 200 nanometers up to 1200 nanometers. According to this arrangement, we were able to detect the response of different types of paintings. And doing this, we were able to detect actually the material that has been used to make these paintings. For this reason, we can say if the painting is original or fake, and this sort of activities, of characteristics. Now, of course, there is a long way to walk if we want to actually develop this instrument to an operating device, a commercially applicable device, and as you can see, as I have written in this slide, we want to test it in different applications, and for this reason, we need to collaborate with entities, with laboratories that use complementary technologies, according to which we can perform interlaboratory comparison tests in order to calibrate, evaluate, and optimize by corrective actions this instrument. I'm afraid I took more time than I was expecting, and now you will allow me to say a few words about what I heard and what we have done during this session. The first thing is that we have heard very interesting sensing instruments. This means we have heard technologies, for example, from iSense that Dr. Amditis presented. iSense is a very important laboratory in the National Technical University of Athens with a huge amount of projects and budget, able to perform, among other things, able to perform cultural heritage activities. We have heard also about CT tomography, X-rays, practically tomography, IR measurements, ultrasonic measurements from Ormilia, and I have to say that since last conference, the presentation of Dr. Karagiannis today was significantly advanced in terms of, not only in terms of the instrumentation he presented, but also the results they achieved during their work, during their research work. Also, I would like to mention the radon detectors mentioned by Professor Xanthos, which is actually significant for not only for cultural heritage areas where tourists or visitors are commuting, but also to health monitoring of people, house measurements and stuff. Apart from that, Dr. Exarchos has presented some smart sensors. He mentioned about the smart sensors and NDT technologies their laboratory is doing, and we know very well the work of Professor Matikas and his team. Apart from that, this session didn't finish only in sensing elements, but also presented the needs and technologies for data analytics. This means, Professor Loutas from Patras University, Professor Pneumatikos also from West Attica University, presented and emphasized actually the corresponding technologies for data analytics. And allow me to say a few words about that. Data analytics are not only artificial intelligence and machine learning. Of course, this is the final goal. But at the beginning, the important thing is to compare results. This means to decrease the uncertainty of measurements. To do that, we need to actually develop algorithms for this purpose. In this way, mathematics are really important for that. Developing artificial intelligence, machine learning, and deep learning algorithms is a crucial procedure according to which we can be more and more closer to the true value of what we measure. For this reason, it is actually a good opportunity to achieve not only monitoring of our cultural heritage, which starts, several thousands years from now, but also to work in health monitoring and observing all this treasure we have in our country. For this reason, this gives me the opportunity to say a few words about an entity that can host all these activities. This entity is the Hellenic Society of Non-Destructive Testing. The previous chair, the previous president of the Hellenic Society of Non-Destructive Testing, Professor Prasianakis, has initiated a lot of work in this field, and we are aiming at continuing such activity. Actually, in this panel, there are two members of the board of directors of this society, the Hellenic Society of Non-Destructive Testing, and we are, it's Dr. Karagiannis and me, that we are inviting all of you interested in in heritage, in cultural heritage technologies and applications to join the activities of HSNT. And why I say that? Because HSNT extended their activities from industrial entity towards cultural heritage entity, as well as medical entity. So all of you welcome to collaborate with this non-profit organization, which can actually promote the collaboration of all these laboratories and entities in general working in this field. And with that, I would like to also invite you to the event, to this annual event, the annual conference of NDT in Ormilia Research Center, which takes place, I think, George, between 9 and 11 of May, which is just after Easter, our Easter celebration, where we will be able to further discuss what we have addressed in this panel. I hope that in the next conference we will be able to discuss advanced technologies based and extended from what presented today in this workshop. Thank you very much.
Thank you, Professor Christophe. Thank you, Professor Christophorou, for the wrapping up. And I would like to point out that, as you have seen from the interventions and from the whole field, we start from physics, mathematics, we cover the whole engineering, but we need to extend this dialogue not only through HSNT. We have to create competence centers that we can integrate all this knowledge and all this expertise so that we can do much more in cultural heritage, and exploit all the know-how we have from other fields like medicine, structural, and so on. Since we are running out of time, we can probably have one question before we move to the next panel or not? I guess not. Yes, quickly.
So, thank you very much and congratulations for your panel. Very, very interesting. I would like to ask the following. AI means data. Yeah? High quality of data. Who is certifying in all over whatever you explained earlier that the data that you produce or that you find to use for the AI is of high quality? At the moment, when we know that there are ethical issues concerning AI, and of course, it has to do with cultural heritage, it has to do with authenticity and identity. It's more than accurate, high quality of data. Yeah.
At the first place, the laboratories follow the orders or specifications of ISO 17025, according to which we are audited for the quality of our measurements. But furthermore than that, we are actually based on what is the soul of this audit process, which is the interlaboratory comparison tests, which means that our measurements are compared with similar measurements of other institutions, as well as with other technologies, other kinds of measurement, which show different responses. For example, allow me to say about, for example, X-ray technologies. The accreditation, the Greek accreditation entity inspects the process. In order to provide the proper agreement, let's say, on these measurements, we have to provide measurements in the laboratory comparison tests with respect to other institutes that perform also X-rays in order to see the difference in the responses. This is applied also in any other technology in which the laboratory is accredited to. But it is not enough. What I mean, for example, Ormilia tests with CT scans, for example, or IR scans, and determines a certain quality of measurement which is accredited by our ESIV. This is the name of the national accreditation entity or system, as George corrects me, which is additionally evaluated by other types of measurements. For example, with optic measurements, with far IR measurements, etc. So, to answer your question, we do two things. First, certified laboratory measurements, and second, interlaboratory comparison tests with similar instrumentation principles, like PTB, for example, in Germany, or INRIM in Torino, or NPL in London, as well as with other laboratories.
Thank you, Professor Chrysophor, for clarifying this. Professor Moropoulou, you have to comment.
So I want to thank you all for your presence, a difficult day in Athens, and for your valuable contribution. And I want to assure you all that within the project Evlogon, we are going to incorporate at the level of non-destructive testing the experience, the know-how and the practical capacity of all the entities you are representing here, because what is most important, apart from the accreditation, is the hands-on approach of cultural heritage, which is assuring what we say, what Marino said, authenticity. Because what you are evaluating has to be the actual body of cultural heritage, whether it is the Holy Sepulchre in Jerusalem or Hagia Sophia in Constantinople, Istanbul of today, or whatever. So that means the open labs we are planning for cultural heritage will be really open, not only to the public, but to you as well. So thank you very much.